Now in Chapter 4, we consider another very important aspect of scientific computing, that is finding roots of equations. So given a function f of x, we're interested in finding the values of x for which the function would obtain the value 0. In other words, when you plugged in that particular value for x, you would get 0 back from the function. Such values are called roots, or zeros of the function. So as indicated down here, my little simple Cartesian coordinate system there on xy axis. I drew a function in here that simply cuts the x-axis in a couple of different points, 1, 2, 3, 4 places between the interval a and b. So we would say then that that function has 4 real roots on that interval a, b. In general, though, for a given function, the roots may be real or complex, but in this course we're only going to focus on real roots, finding real roots for functions. Natural question is, well, how many real roots can a function have? Well, a function can actually have any number of real roots, or none at all. To illustrate that, consider these two functions here, f of x equals sine x minus x, and f of x equals tangent of x minus x. You can easily show that the first one here only has one root, and that is x equals 0. That is the only root, the only value that you can plug in for x and be guaranteed to get 0 back. However, for tangent of x minus x equals 0, there's an infinite number of solutions. There's an infinite number of solutions to that. You could have x, many combinations of x. They'll actually come in plus and minus pairs. So the root finding methods, numerical methods that we're going to consider to find such roots are iterative in nature, very similar to like what we considered for iterative methods to solve linear systems of equations. They require a starting point or a guess, and then what we're going to do is try to narrow in, scope, get a smaller and smaller interval where that root might live to approximate its value. This is called bracketing the root estimate. We're trying to find boundaries. And obviously, if I can find smaller and smaller intervals on the x-axis where it lies, then I must be getting closer and closer and closer to an estimate of what that root is. First method we'll consider very simply is just taking a fact that if we have a continuous function, so if we go back to our very simple coordinate system here, and I draw on an x-axis and I draw on a y-axis, again, as my function wiggles, notice that in some places the function is positive and then it flips negative. So if I can find a place where the function is positive and then I can find a place where the function is negative, then I've got an interval where that function must have a 0. So I've indicated here on the axis here, I know where the function is positive, I know where it's negative, so there must be a root in between those boundary values for functions. So in other words, find me in x1 and x2 where the f has an opposite sign change, there must be a root in that. Very simple idea, but it does make the assumption that the function must be continuous. Our goal then, though, is to shrink the size of that interval so it gets closer and closer to what we could say is a reasonable approximation to the root. Seems like a very straightforward approach, but what are their caveats to this? Well, it's possible to miss close roots if the increment is larger than the root separation, so it's possible just to completely, miss the root altogether. Or you would struggle with determining double roots, for example, like f of x equals x squared. We really wouldn't know whether or not there was a double root there. And then what's indicated here at the bottom is a very common problem that can happen where you have a function that has some type of singularities. Singularities means regions where the function is not defined. And clearly it's illustrated here, the function is not defined at 0, but yet you can see I've produced a value of x0. For f of x0, you've got a negative value in the graph, as indicated here. And f of x1, you actually have a positive value for the function. So it's reasonable to say, well, there's a sign change, and you could be approaching smaller intervals to try to narrow in on 0, but the function is never defined at 0. So it would be, the method would be saying, well, 0 must be a root, but the function isn't defined there, so that would be totally misleading. So there are problems with this kind of approach. But if you don't have those kind of situations, it can be a fairly successful way of estimating a root, and we're going to look at this implementation in a Python file called rootsearch.py, which is on page 147 of your text, which basically searches for a 0 from a user-supplied function f of x in a given starting interval ab. And it would return the bounds, in other words, sort of a set of interval values x1, x2, where the root must live, or none, indicating that it cannot find a root in that interval AB that you gave it. So if we look at that example in the book, here's the root search function that's shown in the book on page 147. Again, as indicated in the book, this function was going to search for a 0 of a user-supplied function, so it's understood the function. The user has to provide the function and an interval where the assumption that there is some interval AB where the root lies. And it will return the bounds x1, x2 of the root if the search was successful. Otherwise, it'll set x1 equal to x2 and equal to none, which indicates no root was found. That's what's indicated in the doc string. Uses the sign function. Very simple function here. Again, the user is going to create a function f which will be passed by name into the Python function here. There's the interval AB, and then it's going to return, it searches the interval in certain increments that the user provides. So the increment has to be provided by the user. In this case, it'll be this value dx. Then you simply set x1 equal to the left endpoint A, evaluate the function there. x2, the next value is just the increment of A, and that we're going to move from the left and evaluate the function there. And while the sign is the same, we'll just keep iterating, so we're going to iterate until we can get a sign change. And the minute we get a sign change, as long as we're not greater than or equal to b, we'll accept it. And again, we'll continue this, and then we'll set x1 equal to x2, f1 equal to f2, set the next guess x2 equal to x1 plus dx, and continue on. While the function is equal to, the sign of f1 is equal to f2. If we get the sign change that we're after, then we will turn x1 and x2. So the while loop is only going to break. Let me just clarify this. The while loop clearly will break when the signs are different, which means I have found an area where there must be a root. So we're going to just keep incrementing x1. It's toggling between x1 and x2 is what it's doing. So we'll start off with x1, then we'll use x2 as an increment, and then we'll set x1 equal to x2, and then x2 will be x1 plus delta x, and we'll just keep moving along until we can get a difference in sign between f1 and f2. Very simple. Okay. And we'll indicate there's an example you can look at in the book as well that illustrates how the user could use it to say find a root of this cubic function here, x cubed minus 10x squared plus 5 equals 0 in the interval 0, 1, and just sort of indicating that what the user has to provide is the function itself. So you can use a definition of the function, use the def keyword, define the function, and return just literally what that cubic is, and then use the root search function to find perhaps the interval. Okay. Notice in this example that the increment here is chosen to be the length of the interval x2 minus x1, which is initially 0 and 1, that was given, that we're trying to find a root between 0 and 1, and it takes tenths. So the delta x there is just starting off at 0, incrementing a tenth at a time until we can get a sign change, okay, and estimate the root. So another approach that we'll consider is what's called bisection. Is another way of narrowing down on a closer and a smaller interval where the root might lie. So this is sometimes called the interval halving method. The good news is it's very reliable, but it tends not to be very fast, and we'll try to improve upon this rate of convergence in another lecture with another method. But for now, let's just look at a very simple concept of, again, playing off of the sign change concept, that when the function changes sign, we know that it's crossed the x-axis from a Cartesian coordinate system. So the idea here is that if there's a root on this interval x1, x2, all right, then we already know that the product of f of x1 times f of x2 is less than 0. Why? Well, because there's a sign change. If I tell you there's a root, there's a sign change, SIGN change. So therefore, the product of those two values must be less than 0. So then the idea here is that, well, let's just see if we can still get a sign change if we half the interval. So we would compute f of x3, where x3 is x1 plus x2 divided by 2, namely the midpoint. So we're just saying that if I know there is a sign change between x1 and x2, then I'd like to just go right into the middle there and then evaluate the function there. And if the product of x2 and x3, for example, is less than 0, then I know that the root is really over in this subinterval and not in this subinterval. Okay. So the idea is to keep halving and halving, and we just have to know on which side after we've halved it to keep finding the sign change. Repeat this until the current interval is just so very small. So in other words, the user provides an epsilon, and when that difference between the two iterates for two successive iterates is very, very small, then you've got a reasonably good estimate of what the root must be. It turns out that we actually can numerically compute the number of iterations it would take to converge given an original AB for doing this bisection approach. And the formula is indicated here. I'm not going to ask you to prove it, but it's important to know it and to be able to use it. That the number of iterations would be this fraction, the natural log of delta x divided by epsilon. Again, the epsilon is the tolerance level that the user has specified that once you've gotten within epsilon in terms of the length of your subinterval where you think there's a root, then you're done. That's divided by the natural log of 2, and the delta x is the original length. It's the original length of the interval you were given to find the root. Okay. So before we look at the it's actually called bisection.py, not bisect. So before we go to bisection.py on page 149, and also an example use of it in 4.3, just wanted to illustrate again what this method is doing. You would start off with a given interval x1 and x2, which would be equal to say a and b, and then you would compute the midpoint and then test where the sign change occurs, and either it occurs on the left half of this interval or the right half. Simply, you're just going to take the product of whatever the function is. F of x3 clearly is still negative, so f of x3 is negative and f of x2 is negative, so the product will be positive. Not interested. But if we looked at the fact that f of x3 is going to be negative, but f of x1 will still remain, f of x1 will still be positive, then we know that we need to continue on this side. Okay? And so we'll just keep halving and halving until we get closer and closer to the root, which is actually there. Okay. So let's look at the bisection.py file to see how this very simple method is coded and then illustrate its use and example point 4.3, which is found on pages 150 and 151 in your book. Here is the bisection .py discussion in the book, and I'm going to actually run an example using it in a minute to illustrate its use. This is on page 149. This module, again called bisection, is going to return an estimate for the root on an interval x1, x2 the user provides, and the tolerance level, which is used to determine convergence. In other words, when the subinterval that it's working on falls less than 10 to the minus 9, less than or equal to that, then it's going to stop and provide an estimate of the root. Now, the design of this function is kind of interesting. It does have another parameter called switch, which is defaulted to be 0. But there is a particular case, as you could read up here in the description, that says in the case if switch is 1, if the user selects that, it will check whether the function's magnitude every iteration where it's getting, it's computing a midpoint and then evaluating the function, then computes the next midpoint, evaluates the function. You could ask it to test whether that function value is decreasing. It's getting hopefully closer and closer to the root. Because if it's not, it might be what's known as a pole. And that's just a very special case of checking whether the magnitude is decreasing each interval. We're not going to worry about that right now, but it's something that is useful in other applications. But if we look very carefully at the bisection function, we can see that that initially it's going to evaluate the function at x1, the left endpoint, and this is very nice and interesting. That again, if you're testing for roots, if for some reason either of those endpoints the function is 0, you're immediately done. You have found a root. So it's very important to just test right off the bat. If f of x1, you say there's a root on this interval. Well, let's start at the endpoint, and if the function is 0 there, return it. You're done. Same thing if you go ahead and evaluate it at the right endpoint. Plug x2 into the function f. Again, f is passed by name, and we're making the assumption the user, given a value, can return the function, and called f. So if the right endpoint forced the function to be 0, you would return it, and you're done again. And then another important test, again, a little error checking here from an algorithmic standpoint. There's nothing wrong with the code, but in terms of our method, is that if the sign of the endpoint, the endpoints f1 and f2, if they're the same, then you don't really have in the function continuous, you don't have a root. So the root's not bracketed, so we would call an error function and return that error. Again, we know exactly how many iterations to iterate given the formula that was on that previous slide, and here's just a representation of that formula that was indicated before, knowing that log is actually ln, is the natural log by default. And so here's just the rest of the function to iterate over I, the number of iterations, taking the midpoint, storing it into a variable called x3. Not the best names for variables here, but we'll cut some slack on the authors of the book, but instead of using x1, x2, we'll compute the f of x3 as the midpoint, evaluate the function there, and then determine if we've got a sign change. If the switch equals equal to 1, we'll be testing whether the function is decreasing. Else, we're simply looking, first of all, did we get lucky, compute the root immediately. So again, compute the midpoint of the current interval where we think there's a root, test to see if it's 0 there, because if it is, return it, you're done. Otherwise, make sure that there's a sign change. This is testing if the sign of f of 2 is not equal to sign of f of 3. This is the right side of the interval. Then set x1 equals to x3 and continue on. Else it must have been on the left side. Set x2 equals to x3 and so forth and continue on. And again, you're going to be iterating this, all right, this example until you've hit the number of iterations in, and then you'll finally compute the midpoint at the very end, and that'll be your approximation to the root. So the example we're going to do to use this bisection.py file as well as root search is to find all the zeros of this function f of x equals x minus tan x that we mentioned before but on the interval 0 to 20, not including 0 and 20, all the roots in between 0 and 20 using bisection. And keep in mind there are singularities for tangent of x. It's singular and changes sign at all pi over 2, 3 pi over 2, and so forth. So to prevent the bisection from treating those points as roots, that's where we'll set switch equals 1. That'll avoid choosing those particular cases as roots. So setting the example code up is fairly simple. You'll just have to first of all import root search, import the bisection module, define the function. Again, tangent lives in the math library, so you could either import math or specify it this way. So you don't always have import math function and then specify that we're using math.tan of x, and we're returning x minus that. And then here's a nice little way of setting a tuple here for defining the values of a, b, and the delta x in terms of a tuple, which is kind of clever. Print out that we're going to print what the roots are and then have a while loop. That's while this is true. We're going to continue to find a bracket. First of all, we're using root search just to get an initial bracket, an initial guess at a root, and then use bisection to hone in on it. So this is kind of a nice little hybrid approach. Use root search just to start off with 0 and 20, a is equal to 0, b is equal to 20, and just give me a first guess at a root from say starting from 0 moving to the right. Put that subinterval into x1 and x2 and then start bisection. And then just continue this process moving along between 0 and 20 and trying to find all the roots. All right. It's interesting to know that this while loop is only going to break when you hit this break, which only happens when the case that root search is going to return none and for x1 and x2, that when it cannot find any more roots. Again, it's always starting from whatever a and b are set to, and then the delta x is 0.01, so we're moving in increments of 1/100th from 0 all the way to 20, finding a bracket around each one of the roots, and when it can't find any more is when we'll actually come down here, print done, and break. All right. So again, if it's not equal to none, then we're moving the a, the left endpoint, to be the x2, and so the next time we'll keep moving to the right, so to speak. So a starts off here as 0, we find some root where it's x1 and x2, so we'll let a be x2 next time, and we'll keep moving to the right till we get all the roots. And as indicated in the book, here are all the roots between 0 and 20 for the function x minus tangent of x. So let's look at the code itself and see graphically how this makes sense, that those are the places where the function would hit the x-axis. So here is the example 4_3.py file that I'll provide on Blackboard. By the way, root search and bisection are also there as well, so all the modules that you've seen so far in this chapter are available on Blackboard. And so in this particular Python script file, you can see after doing all the imports of all the library routines that we need, I've defined the function to simply return x minus tangent of x. Okay. Again, now in the book, notice they had math.tanx because they only said import math. I'm specifically telling the interpreter from the math library import tan, so I can use it directly. So again, what you noticed in the book, it just said import math. So if you want to, if you're trying to access a particular function that way, you're going to have to say math.tanx. You don't have to do that if you're willing to list the explicit names of the functions that you're importing. Okay. So the rest of the code looks pretty much like what you saw in the book. I just said while 1 rather than true, 0 would be taken as false. So we'll just do this until we can finally get none to come back from x1 in calling root search. And the rest of the code is just simply to set up arrays, x data and y data, so we can plot what the function actually looks like. All right. So I'm just going to use matplotlib to actually draw the function. as we're sampling values here, just on the interval 0 to 20, I'm just going to plot the function so we can see if in fact those areas where we saw in the book where it determined their roots, if it made sense. Okay. So we'll go ahead and run this because the Python path is specified on this in that script, and the roots are there. I'll have to set the local host on this machine to be able to plot it. I'll do that in just a second. But before I do that, let's just review again that we did numerically, starting with the delta x being 0.01, started from 0, moved all the way in increments of 0.01 to find all the possible roots. And we have the 6 roots that that function x minus tan x has on 0 to 20. So now let me, after I've set the probable localhost environment variable so I can see the display of the output. Again, I've got this on Blackboard to use. It actually uses matplotlib to plot the particular function values between 0 and 20. And this is really nice for verification purposes because, again, what we've got listed over here are where the roots are. And you can see 0 is a factor root. There's supposed to be a root about 4.5 if you follow the curve here where it cuts, again, this is the x-axis right here, so it's cutting about 4.49, and then the next one comes around 7.72 right there, and then the next one comes a little bit about 10.9, almost at 11 right there, hits exactly at 0. Then another one hits around 14, that's about right there, and then we have to go a little bit farther out, around 17, to hit it. So really nice illustration of seeing the fact that there are places where the function is going to be hitting the x-axis. Again, it's nice to be able to use matplotlib to get some verification. Of course, you could imagine plotting values of the function to define subintervals to narrow in for estimates of the roots using routines like bisection.